The quiz only has 10 questions. I couldn't find anything else to ask, so I just weighted everything a little bit heavier. Now you need to be able to define enthalpy. Use endothermic and exothermic in your definition and be thorough. This is a college level course. I need to see a college level definition. Now the first question I have on the homework is calorimetry. So that you'll need to be able to solve a question like this as well as one where the bomb calorimeter has a heat capacity. Now in this one we're told that the heat capacity of the calorimeter is negligible. So it's something we can basically ignore. Now, what we need to do, though, is parse out the information we need. So we're told that we have 10.7 milliliters of a 0.13 molar HCl solution. And we have 10.6 milliliters of a 0.48 sodium hydroxide solution. Now, both of them are at an initial temperature, so our TI is 21.7. And that's added to a coffee cup calorimeter. The temperature of the mixture will reach a maximum, so the T final, of 30.0 degrees Celsius. So what's the amount of heat produced, specifically in kilojoules, by the heat absorbed by the calorimeter is negligible. Remember that the Q of the reaction plus the Q of the solution plus the Q of the calorimeter all equal 0. Because we're told that the calorimeter is negligible, I'm going to just cross this one out. So the Q of the reaction plus the Q of the solution is equal to 0. Now if we subtract the Q of the solution from both sides, then the Q of the reaction is equal to the negative Q of the solution. We can calculate the Q of the solution. Now the Q of the solution, or the heat of the solution, is going to be equal to the mass of the solution times the heat capacity of the solution times the change in temperature. Now the mass of the solution, because we're dealing with aqueous solutions, we're told they're aqueous right here, we can go with the general definition of density of water is 1.0 grams per milliliter. That's close enough for what we need. So if I add together my milliliters, then I have the mass of the solution. So adding those together, I get 21.3 grams now of my solution. The heat capacity of the solution is 4.18 joules per gram Celsius, and that you need to memorize. Then we have our delta T. Now delta T is going to be T final minus T initial. So 30.0 minus 21.7, I get 8.3 degrees Celsius. Multiply all of those things together, and I get 738.98 and then more digits, joules. Now we're told kilojoules, so 0.73898 kilojoules. That is the Q of my solution. Now the negative Q of my solution is the Q of my reaction. So going back to the question, it doesn't give me a decimal place to aim for here. So you really should only have 2 significant digits due to these 2 significant digits here. Number 2, calculate the standard enthalpy from the data found in the table. It says at the end of the quiz, it seems to be right below it for convenience. The data will be calculated as kilojoules or kilojoules per mole. Now when we go to calculate one of these, we need that balanced chemical equation first, and that was solid aluminum reacts with iron 3 oxide to form aluminum oxide and iron. So we have the H of this reaction, the delta H of the reaction, and that's going to be equal to the sum of the H's of the products minus the sum of the H's of the reactants. Now it's helpful if you put the products in parentheses, so we need 2 times our aluminum plus our iron compound. Oh, I did that backwards. Products, then reactants. So I need my aluminum plus 2 times my iron minus my reactants. 2 times aluminum plus my iron. Now in its elemental state, we should have 0 for our delta H. So the heat of formation, the enthalpy of formation of solid aluminum is 0. So the aluminum oxide compound I need is a negative 1,669.8. I'm going to drop that in right here. There's my 0. This iron is also going to be 0. I'll show you that here in a moment. So here's the enthalpy, the standard enthalpy of iron, solid iron is 0. And here's the oxide compound I need. Again, delta H is in the first column. So I'm looking for the negative 824.2. Now let your calculator do the work if you get confused with subtracting a negative. But what you should end up with is a negative 845.6, and this is kilojoules per mole. So coming back over to my quiz or my homework, I would type negative 845.6, leave the units off. Number 3, for this reaction, we are given the enthalpy of the reaction is this value, a negative 3.6 kilojoules per mole. If we have these conditions, so we have a volume of an HCl solution and it reacts, then what's the heat energy that is produced? And we're told to report to the hundredths place. So first I'm going to write down that balanced equation, because I'm actually going to need one of those coefficients. Okay, I'm going to leave the phases off for the time being. So the H of my reaction, I am told, is a negative 3.6, and that is kilojoules per mole. Now I'm told that I have 1.5489 liters of an HCl solution, and that HCl solution has a concentration of 1.5 moles per liter. So I have these moles of HCl. Now I can use this value as a conversion factor. So my negative 3.6 stays with kilojoules, but how many moles does this mean? Well, the coefficient here in this balanced chemical equation that this was used in order to calculate this value goes here. Remember, the absence of a number in your balanced equation is a 1. So when I multiply all these things across, I get a negative 8.36 kilojoules. So what I would report here is negative 8.36. There is no space, and do not include the units in one of these questions. Now, number 4, is the above reaction endothermic or exothermic? Well, this is an exothermic reaction. When we have a negative sign for our enthalpy, that is an exothermic reaction. That means heat is a product of our reaction. And number 5, we're going to calculate standard molar enthalpy of formation from the following data. So this is a Hess's law equation. And what I'm going to do is write these down real quick. I'm going to leave the phases off just because this gets messy enough. So I have my N2 plus my 2O2 reacts to form 2NO2. I'm going to put my delta H's over here, 66.4. And these are all going to be kilojoules per mole. And then I have 2NO plus O2 reacts to form 2NO2. That's a negative 114.1. So we have to dissect the language a little bit. We're told we want the standard enthalpy of formation, so of formation of this compound. So immediately I know I need to flip this around. So I need the 2NO plus 2O2 over here on the product side. And what I want to do is I want to end up with an equation. So when I flip that around, I change the sign on the H, so I'm going to erase that as well. What I want to end up with is an equation that has elements reacting to form my target compound. So here, if I take these two equations and add them up, because my two NO2s are going to cancel out. But I'll show you that here in just a second. So I'm going to add them up. So my reactants stay on the reactant side. So I'm going to cross out what's alike on both the product and the reactant side. I'm effectively subtracting 2 NO2 from both the reactant and the product side. I'm also going to, there wasn't a 2 there. There wasn't a 2 there. I'm also going to subtract 1 oxygen from either side. So what I end up with is N2 plus O2 reacts to form 2NO. Now when I add these H's together, I get 180.5, and that's kilojoules per mole. But the question specifically said formation of NO, not of 2NO, but of NO. So I need to divide this equation by half. When I divide this equation by half, I also divide my H by half. So the answer you would report is 90.25.